Hello, welcome back. In the previous segment, we discussed the DSA algorithm. In this segment, I want to show you an interesting bug that was detected for elliptic curve digital signature algorithm. Although we didn't discuss elliptic curve in the previous segment, the same type of bug that is present in this particular implementation of Java actually is also relevant to digital signature algorithm called DSA. But the DSA algorithm actually implemented correctly in the Java version. It checks the input parameters properly before validating the signature. So to make the long story short, what you're seeing here is an interesting article that says a cryptographic blunder in Java enables digital signature forgery. The root cause of the problem is that if you are trying to find inverse of zero, right, the implementation returns zero. However, that particular division by zero or finding mod inverse of zero turned out to be a significant flaw in the elliptic curve digital signature algorithm. I will show you that the same problem can also occur in DSA if the implementation is not checking for division by zero error. Okay, so let's take the DSA algorithm, right? This is the implementation of the DSA algorithm in Java. One particular, we talked about the algorithm details during the last segment. In one particular important check that Java is doing here, among many important checks, is that it checks whether the signature pair R and S, right? Signature is made of two things, R and S. They both are positive, meaning greater than zero. Okay, and below the value Q. We talked about all the details of R, S, P, Q, and so on in the previous segment. So for now, assume what happens if one of these checks is not present. Let's say I remove this, right, in my implementation, or implementation forgot to check this correctly. I'll show you that any signature, right, zero as a signature will be accepted by the implementation. So in particular, I will be constructing a digital signature where I will put signature to be zero or to be one, and then I will pass the digital signature verification. Okay, that is the core idea of my demo. Let's go ahead and get started, why that will work. So I'm going to share my proof of concept DSA implementation, right? And show you exactly the problem that I'm trying to demonstrate here. So in the case of signature verification, right, you have the verify function here. All of these parameters, P, Q, G, they are group parameters, usually NIST standard or something along the lines from the RFC. You will get the P, Q, G value. M is the message to be signed. R and S are the signatures, and Y is the public key. Okay, P, Q, G are also public, by the way. R and S is a digital signature pair, which is produced by the signer using the private key. Okay, so at the time of verification, right, the verification must check a few things about R and S. Okay, let's say if it is forgetting to check the fact that S is greater than zero. Okay, and I commented it here, right? Okay, so in this case, let's say the implementation is not checking S being zero. So which means when S is zero, and I'm going to introduce a bug here in the mod inverse, right? Mod inverse of zero is not defined. It should be exception thrown or something like that. But the bug that was introduced in Java is when zero is passed for the S, right? W will be zero. So the bug is over here in this place. If S is zero, right, attacker is sending S to be zero. Mod inverse has a bug. It will send W to be zero. So W will be zero. That means when W is zero, right, U1 will also be zero because you're multiplying by W. And your U2 will also be zero because you're multiplying again by W. Since U1 is zero, U2 is zero. You know, if you remember, anything raised to the power zero will be one. Similarly, this is also one. So this whole thing is one. So this means V is one. So all the attacker has to do is send whatever message he wants to sign, right? He doesn't know the private key, but all he has to do is pick up his message M. The signature will be R, S. What kind of R will the attacker choose? R to be 1, S to be 0. If that's the case, right, V becomes 1, R becomes 1. So because that's the reason why R is 1. Okay. S is 0. That's the key point. When S is 0, we know for sure V is 1. So R is something input, right? User input. R and S are user inputs. Okay. So all the attacker has to do is generate a signature with R, S to be 1 and 0 respectively. Whatever message they wanted to get signed, they can, whatever message they want to verify, they can get it verified. Without knowing the private key, they're able to generate a signature. Okay. In the normal operation, right, you would be able to sign only if you have the private key X. We talked about X during the previous segment. Okay, this is the flaw we are going to exploit. Let me show you one more thing very quickly. I have introduced a bug in the mod inverse similar to Java's bug, right? In the numutils implementation, I introduced a bug. If A is 0, return 0. This is a bug. Okay, so I'm going to now demonstrate how I can generate digital signature without private key. So I'll be using the RFC, for example. Okay, you need to be careful which RFC to use and group parameters and so on. But for the proof of concept, I'm going to select this particular PQG, which is published online, right? From RFC standard 7919. Let's get into the Python shell and we'll quickly do the demo. So we have all the public parameters, P, group parameter, P, Q, and G. We talked about all those P, Q, G in the previous segment. So watch that out. Okay, now I'm saying, suppose you would like to do a digital signature of M without knowing the private key. This is a forgery is the message. And I will set the R to be 1, S to be 0. R and S are digital signature, which you can only get if you know the private key. But in this case, no private key. Let's do the verification, right? The verify should successfully verify the, okay, I need one more random number. I can pick anything because the verify implementation requires the public key Y, okay? This is basically the syntax of verify. We saw in the previous segment how to verify. We need a Y. We have everything. Y can be any number. I'm just going to pick any number in this case. I'll show you why. It doesn't matter. Rand range. Just pick a random number from 1 to Q minus 1. Q is also public. All right. So we got, one moment. Maybe I made a mistake. Rand range. Oh, I didn't include. Okay. From DSA import or import star means everything will be imported. And now I can do my Y. And everything is now ready. I'm going to call the verification function. Okay. So verification function will verify successfully. For verify, you don't need the private key. For digital signature, you need the private key, but the signature in this case is forgery. R equal to 1, S is equal to 0. Yeah, you see, digital signature went fine. It says true. The reason why it went fine, we can go back quickly in the implementation, right? First of all, two things. Remember, mod inverse is buggy. I introduced this bug. If A equal to 0, return 0, that means any number division by 0 is 0. That's basically an approximation to think about. So this is a bug. I will remove it to avoid this. Also here in the verify, right, I introduce a bug. Don't check for the value of S. If S is 0, we are in trouble. Okay, so when S is 0, W becomes 0 because of the bug I introduced in the mod inverse. When W is 0, 1 will also be 0, U2 will also be 0, but V becomes 1. So that's the reason I have selected my R to be 1. Okay, R is something that I control. Y is the public key, which is publicly available. So is PQG. Attacker can choose any M, and the signature can be just as simple as R being 1, S being 0. Okay, that's basically the reason why the signature verification worked. Remember, signature verification only works on public data. Everything is public. P, Q, G, M, Y is public. R and S can only be produced by somebody who knows the private key X. But in this case, because of the flaw here, one can perform digital signature forgery. That's all. So the implementation shall consider this. Now we should fail. Let's do that. Okay, I need to copy the PQ, all of the RFC data. Okay, and now I will set my message to be, this is a forgery, right? It doesn't matter whatever message you want to type. It will be hashed using SHA. Okay, this is a forgery. And then I need my R and S, right? I said R to be 1, S to be 0, and I need a Y random, any random Y I placed. I can just, Y has to be a public key. In any case, we will just select a random range, right? And now, if we call the verify function, it better fail because we are checking whether yes is actually non-zero. Yeah, you see, assertion failed. Okay, that's good. All right, so if you go back to the Java version now, right, of the implementation, let's look at that quickly. This is not elliptic curve digital signature algorithm. This is regular DSA on a prime field. Okay, Java already took care of this bug. Okay, well, it's already play a part of the implementation. It checks the signature is greater than 0 and R is greater than 0. Okay, and if you look at this particular article, right, this particular article is specifically for elliptic curve cryptography in Java's ECDSA implementation. They assumed that mod inverse of 0 is 0. Therefore, 0 as a signature worked fine in this demo. Interestingly, same concept applies for DSA, but it's taken care already because of that check. That's all. Thank you very much for your attention.